All right, so it's great to be here. It's kind of an unusual topic for me. We don't do much in GPUs, so we're newcomers to this. So the topic will be fairly simple, but I think it's still interesting and it's non-trivial. We actually don't know the best answer to it. This is some work I did together with my student Dénes Molnár. You will get some physics. So this is particles and viscous hydro. It's the physics part, and you get a little bit of mass and what it involves, and then we go to how to try to do this in parallel. Oh wait, I'm pushing the wrong thing. What am I doing? So the physics question is, why do I care about particles from hydro? So we get to that, and then what mass it involves, and how we solve it on a single-threaded algorithm, and then the bulk of the matter is how do we get to a multi-threaded solution, and what is our experience, what challenges we found, what we could manage to do. Yeah, perfect. So okay, heavy ion physics. Gergely had the slides. So we collide. Oops. Oh, this actually works now. It didn't work too well. So we band two heavy nuclei together, and we want to create a system called coagulum plasma. It's a new form of matter. This is a cartoon of the collision. Nuclei, Lorentz contracted, approach each other. Something happens. We believe the plasma is formed here, and then the plasma breaks up because the density is low, and eventually particles reach the detectors, which we call hadrons, pions, protons, kaons, and so on. So, as a theorist, you might try to model this, and hydrodynamics is if the plasma is thermalized or near-thermalized, is a good framework. And hydrodynamics could be used to simulate what happens here if you have some initial conditions, then you run hydrodynamics, which is in terms of field in space-time. So, for example, energy density, pressure, baryon density, viscous quantities like bulk pressure, shear stress, and so on. And it's good, we like this model because it connects to the information we want to infer. This cares about the equation of state, about viscosities or acceleration times, and that's what we hope to learn from comparison with data. But you don't see these fields in the detector. You have to have some additional theory which converts these fields to particles. And that's the part which is underappreciated, but the main focus of the talk. So the problem is, it's non-trivial. What is this particle distribution? If you believe you have hydrodynamics, and there's this notation to relativistic theorists like it more, but people who are not physicists, but bear with me, this is energy momentum tensors, so energy density, pressure, shear stress, and so on lives here. This is where the various conserved currents live, like baryon density. And hydro gives you these things, but you want particle distributions, this so-called phase space density F, which is known from kinetic theory. And if your kinetic theory has actually a means from kinetic theory to compute these quantities. If I know the distribution of particles, I can do some integrals in momentum and I get the hydro quantities. The problem is I need it backwards. I am given hydro quantities, now I have to come up with these F's, the distribution functions. If you are in equilibrium, so you're doing so-called ideal hydrodynamics, zero viscosity, no entropy production, and so on, really nice, then there is just as much information on the hydro side as what I need to build up thermal distributions. I can do this, perfect, that's boring problem. The interesting question is what to do when you are not exactly in local equilibrium, because you have viscosity, you have additional terms here, non-dissipative terms here, so it's non-equilibrium terms here, which change the hydro information. It's in the hydro fields, we know this from the simulation. Now you have to also change the particle distributions accordingly so that these integrals check out. The problem is you have infinitely many ways you can do this. And without additional theory, you are just doing ad hoc games. And that's, so what do you do? So it's actually, I just want to tell you, this is actually important. So Gergely didn't mention this, it was one of the Alice slides, one of those plots are actually about this elliptic flow. It's a quantity which tells you if you have this is two nuclei go in and out of the board, it's an off-central collision, so you have some coagulum plasma maybe in this green region. And then this plasma expands, and it's kind of nice feature of such systems, even called atom systems, that at late times you get actually a momentum space anisotropy from such a coordinate space initial shape. You can characterize it with an eccentricity initially, and the final eccentricity and momentum space, we call this V2 elliptic flow. And you can measure this as a function of some momentum variable, that's a detail. The main point is there are measurements of this black and open and closed black points, and there are calculations based on hydrodynamics. And what you can do is you vary the viscosity in this hydrodynamic code. Actually, it's viscosity to entropy density, but that's a detail. And you could read off what works against observation. You could say, aha, shear viscosity to entropy is maybe 0.1. Now this is all great, but this relies on this conversion to particles. And as we showed, depending on what model used to convert to particles, these hydro results, plus the, of course, hydro doesn't have a result on this plot. Hydro plus the conversion model has a result on this plot, and these curves change, so you will expect a different viscosity. So it is critical to use the right model. Now most people use some ad hoc parameterizations, there are a gazillion of those, and they are common in the sense they're not based on any physics. They are just such that convenient functions you can integrate and make sure it things check out. Now what we advocate, and a couple other people do, is you could try to calculate this from kinetics theories. It's linearized kinetics theory, lots of caveats and so on, but the good thing that there is a framework in which microscopic interactions uniquely give you these quantities, because it's essentially the question, you stir the soup goes out of equilibrium, but if you wait relatively long enough, then only the slowest dying mode lives in the soup, and this mode I can calculate from kinetics. And it's complicated, I won't show you much equations, but in the end it boils down to an integral equation. One scalar function of momentum is what describes these viscous corrections, and there is an integral equation for this which spits this out. There is a source term, which is known, it's coming from gradients, and then there is this, all the kernels are known. The question is, what is this chi function which solves this kernel? Now, this is nice, but the way you solve it normally is you turn it to a variational problem, which in physics is very common. You can find instead a functional, which depends on these unknown chi functions. Everybody else is known. You have to integrate lots in momenta, and if you maximize this functional, the maximum gives you this chi. Which you, of course, you then do a basis. It's like quantum mechanics, solution finite states kind of. You make a finite basis. This becomes a finite dimensional maximum search and basically a matrix inversion problem. You have to compute the matrix and also this vector. Now, this matrix is the hard part in this problem to calculate. It involves 12 momentum integrals of some kernel. And then you plug in here various basis functions. Now, with some work, you can bring down the 12 integrals to 4, but those remain, and you have to do them numerically. So, you know, you could say, 4 integrals, it's not really a big deal, and indeed, to single-threaded computation, we can do this, and we do this in adaptive routine from the GNU Scientific Library. Adaptive 61-point Gauss-Kronrod works perfectly in each dimension. So you have nested integrals, and each one of them use adaptive integration. And this is basically based on the 61-point formula. Everybody hopefully knows roughly what quadrature is about. You have an integral, and your idea is to sample at special points, and you combine the values with special weights. And these are points and weights are engineered such that you get high precision for certain class of function, in this case polynomials. And you do this, the nice idea in this formula that you take the very same 61 point, but evaluate only at 30 places, and you get a less accurate result, but then from the difference you have an error estimate. And this is done automatically for you, and then you decide what error you want to reach. If your error is not reached, then it starts bisecting your interval. It takes them halves and halves and halves and halves, and always bisects the interval with the largest error, and this just iterates this for you until your error target is met. It's beautiful because you just fire and forget. You do it in 4 dimensions, so x, y, t, and z just happen to be called variables. So you have an x integral which starts taking 61 points, and for each one of them goes the y integral, which for a fixed x takes 61 points, then this for a fixed x and y takes 61 points, and so on. And then once you have here this converge with various bisections, then you have a point here, then you go back again, and so on, and eventually you build up the result. It's beautiful, it works nicely in single-threaded, but this is a dependency. I cannot refine it. I cannot decide whether to make new intervals on this level, say the 3rd level, until I actually computed the result on the 4th level, which itself may require lots of bisections. I can always do the next step, but I cannot do multiple steps. It's like a tree. I go down the tree, but I cannot just jump up. I have to finish everything at the bottom level. Now, why do we care about actually multi-threaded? Well, we're actually happy with this. So in some sense, we have a computer cluster, we could run this. It's just that it starts getting a little bit cumbersome. 25,000 jobs being sent in and so on, and they all run for half an hour. It's kind of boring. So we thought, since Gergely has this nice resource here, maybe we could also learn to use this. And maybe, on one hand, we learn about maybe better algorithms. On the other hand, we might have another resource that we could use. If we don't get to a cluster, maybe we can get to this. Now, this is my feeling as a newcoming user to this GPU problem. So, yeah, so you have these crappy team of players, which kind of miserable in some sense to look at them, but your only hope is that they have many of them. So maybe you can still beat a good team because you have many such players.
On the other hand, you are kind of straitjacketed. I cannot do on this GPU in programming what I really want to do. Certain things like passing a function pointer, impossible. It's just nuts, but anyway. So I feel it a little bit restricted also on the development side. I'm pretty sure it was much worse when people started 20 years ago, but I still feel it's quite restricted. So this is the kind of ideas that we did. So idea 0 was that, so I have to do integrals. Each integral requires 61 evaluation. Of course, I could trivially parallelize that 61. So I could go back to the inner level, and I say, okay, we do, push the wrong button. So this 61 we do in one shot, and I could do that, and I gain a factor 61, but that's not enough. I really want to go in the thousands. So I don't find this exciting. So the next step was, okay, how about trying to do 2 integrals? That's kind of like factors 3,500. And the problem is, this was an adaptive algorithm. It starts bisecting in funny ways. I cannot just do one shot. So in fact, maybe we switch algorithm to 2D Simpson. It's really nice. It's agreed with nice little weight structure, weight patterns are engineered to kill Taylor expansion terms. So it gives you like epsilon to the 4 accuracy. You can tile it if you have a larger region. So it's 2 by 2. You tile it next to each other. You get the weights. Perfectly calculable, perfectly parallelizable. And even you can do the weights without conditionals. It's beautiful. It's perfect for GPUs. We tried this. So each GPU computed one such integral. So fixed value in x and y. On a GPU with each thread was computing this. And this was all beautiful. The problem was we didn't hit accuracy that we wanted. We need about 11-digit accuracy. And this Simpson just converges so miserably slow that it was just not possible to reach. So it was beautiful. We had it once, but bad luck. So I said, fine. So we have to bite this bullet. We put the nested adaptive graph control on the damn OpenCL. So it's in there. Each thread does the 2 integrals, and for different x and y. And then the idea was that we drive this from outside with inputs on which x and y you should do these 2 integrals for. Now, this kind of stuff's nuts because it requires local storage. We keep bisecting. The good thing is we made a plot. So this is the counts versus how many extra bisections you needed for each depth. So for the innermost depths, I normalize this so you can get a rough feeling of how many such integrals there are actually being done. So this is the red line, the innermost integral. You kind of see most of the time I only need 1 bisection. So it's like 2 attempts. And maybe there's a tail that goes up to 10. If I do the second most integral, that's the t integral, that's also very similar. So there is a chance I don't need much gain, don't need too much iterations inside. I also don't need much storage for it. Whereas the other 2 integrals are on the orders of tens, which are much more these outer integrals. And you can kind of see I do a billion integrations for the inner core times 61 function evaluations. So it's on the order of 10 to the 11 function evaluations what it took to do this. So there is a chance to do this. Here is actually the code. You can do it. You can a little bit engineer it because you try to eliminate as many conditionals as you can. Basically, this is a loop. You have some interval that you integrate over this. You get some initial value. And if the error is too big and you still have storage to store bisections, then you start taking the worst case bisection. Unfortunately, this needs 1 conditional. Then you take left and right, integrate them, update error estimate, store the results again, and keep looping until so 2 conditionals, but that's the closest I could get. And it runs, and it's really nice. And then on the outside line, I'm trying to drive the x and y integrals from outside, because now I'm more or less good with the inside, but I still have 2 more dimensions to do. And the other integrals, well, if you didn't have to do bisections, you have 61 times 61 points, x and y, you could do them in one shot now because I send them on each in different thread, and then I'm done. The problem is, what if I find that the lower level, the y integration, needs an extra bisection for this given x1? I could find this out because I make my error estimates. I make this new information. This is a nice validation, almost like 4,000. But when I find this new bit of information, I cannot do anything on the top level until I did this refinement. And suddenly I'm back to that. My next step, if I do a calculation, is only order 61 at best, because I'm operating on this lower level, trying to refine the values. I lose it. The first shot is great. The next shots are very slow. And we struggled a lot with this, what to do. Now, the idea would be either to try to guess ahead and start bisecting the top just by guessing, because you don't have complete information. We couldn't come up with anything great. So the only thing that seemed to work for us, we just came up with this idea that instead of thinking in terms of 1-dimensional slices, we really should think of 2-dimensional regions. We do a Gauss quadrant in 2D, and we start dissecting this 2D region based on what the error estimates are. So this is, for example, first you do this, maybe the error is larger here than there, so you cut here, because the error in x direction seems to be larger than y. Then you cut here, then you cut here, then you cut here, and just zoom on to the most relevant part of the integral. So this is what we implemented, and this is how it looks like. So you basically take a tile, and you have 61 by 61 points. You could do Gauss Cronrod in two different, you evaluate it once, but then you sum them up differently depending on whether you thought first you integrate over y and then over x, or whether you integrate over x and then y. And if you do this in the Gauss Cronrod, you get two different error estimates. The result is basically the same. Same points, same weights, but the error estimate is different. So, and then based on, you get an x error, so if you do the last integral in x, you get an x error. If you do the last integral in y, you get what I call a y error. You could conservatively estimate, and this is heuristic, I didn't have numerical analysis really backing this formula up, which should be done later, that you take the maximum for the error. But we know which, if you ever have to cut this tile into two because there is too large, I will use these two values to guess whether the x direction or the y direction is more sensitive. And that's what we do. And now we have an algorithm which has always a 2D tile which we can send out to OpenCL to compute as one, but the iteration of this runs on high level on CPU. And this is what we get at the end. So I don't know where I'm with time, but fine. If it's fine, it's faster, it's faster. So we did bulk viscous delta F with a certain basis which bases on powers of square root. It just happens to be a useful quantity based on our basis, based on our densities. Polynomials converge very poorly for our problem. The solution is close to square root of x, and that's why this is what it is. And I have a 17 by 17 problem. So my matrix that I'm computing has 289 elements. And then I do this thing, and I have two integrals run in the innermost on the OpenCL, and the other two are run by this 2D bisection iterative thing running on CPU, and it keeps calling OpenCL for the innermost two. And this is running in this after on the Wigner GPU lab here, and this actually turned out to be a CPU, which was a little bit of a surprise after a while, but it is, okay, fine. And it has 32 cores, and in 30 minutes we get the full matrix. It has 11-digit accuracy, but you will not see anything, so I truncated all. This is kind of a large matrix. It's symmetric, which gives us a good cross check. You physically know it must be symmetric. But you see the numbers kind of vary from order 1 to 10 to the 9. So this is really a kind of a funny matrix. And you can compare this to a single-threaded calculation, which took 10 hours, so 20 times more, at Purdue back in the Core i7. This is in C++, the four-nested adaptive Gauss Cronrod. And the relative difference in the results is what is plotted times 10 to the, so what is plotted is, the difference is this number times 10 to the minus 13. So you see the worst number is this minus 180, which is relative difference between the two calculations, 1.8 times 10 to the minus 11. So that means the accuracy is really reached, that's what we wanted. But you have to run 20 times longer, which is kind of in ballpark, in its proportion to the number of cores, very crudely. And if you know A and B cores are kind of slower than inter cores by factor 2, then maybe we lost 50% in efficiency. But that's kind of okay. So it's not totally crazy to do this, and we are hoping to put this on the real GPU. Now the problem is we tried, we figured out there's actually GPUs in there, and we tried to compile, and simple tests do compile in their own GPUs, some of them at least, and they're fine. This particular kernel doesn't want to compile, and unfortunately, there's not much diagnostics to get back, except, okay, the program failed. So I don't know where we are right now. We're hoping to get through this, and the experts here eventually understand what this is. But that's it. So we are trying to put it on the real GPU to just see how things scale, especially the conditionals and the adaptive part. Sometimes you get NANs even on this particular, everything's only on CPU. I don't understand where this comes from. There's nothing in the code that should give you NAN. Maybe the number representation is even the initial evaluation, not with iteration, just the initial 61 by 61. Sometimes it's NANs. I think this is some issue with how things are being compiled, how the numbers are represented. It's rare, and even if it is there, it could just be run either on CPU or try to tweak a little bit parameters. That's fine. So I'm happy with a little bit of error as long as I'm doing things fast. Of course, we want to do it for shear viscous delta too, which is harder, more complicated kernel, longer to evaluate. Now we have a new algorithm which put these 2D bisections. We could also run a single threaded and try to figure out whether it's better or not. The nice thing is it really needs only 10 tries. So the previous one needed 10 in each dimension. So in 10 in each dimension, roughly what I needed to get things right. Here in one step, I get just 10 steps, I get the right result. But of course I'm paying more price because every single time I'm evaluating the whole 2D Gauss-Kronrod and not just the single one. So I'm not so sure how this performs, but it's interesting. But the longer term, the interesting part, especially for somebody in numerical math, is this is only, okay, 3,700. It's not any n. You cannot really scale up to any n. To do that, I was thinking about how to do this. So the problem is really, you would have to either bisect multiple intervals, not just one little improvement, but try to guess many places at the same time where the potential improvement is good. Or you take one interval and try to cut it to many spaces so that you get a sudden larger improvement. I don't really know how to do this. It's kind of like guessing ahead. But I'm pretty sure other fields try to deal with this problem. People who design CPUs do this all the time. So I'm hoping to learn from other people. It kind of feels like this problem with the beta ships. So suppose you have beta ships, Samara. If you know if you're a person, the ships could be anywhere. So it's roughly like n squared problem with this n by n board. You need about n squared tries. Once you have one, in order one, you sink the ship. But you have to have n squared tries. Now, suppose I have more torpedoes, which is what I have here in each round. I could do more. It's like I could have like fluke shots. It's okay as long as I sink quicker. And also, I have to have some hints over. It's not just order and randomly shooting. I have some ideas about where the ships might be after each shot. I just don't know how to use this probabilistic information to my advantage, that I still fire many times in each round. And if I could do this converge more, if anybody has a similar problem already solved, I would be very happy to learn from it. Other than that, this is it. So it's important to realize that any comparison of heavy ion simulations, hydrogen simulations, or heavy ion physics to data requires this model that you convert the fluid to particles. You can do this intelligently if you use this delta functions, phase-space corrections, which come from kinetic theory. And single-threaded computation, straightforward problem. We know how to do this. You just have to wait long in a cluster, but it's doable. We're not begging for GPUs. We could solve this problem with computing, just have to wait. But it's kind of exciting to do this on GPU, and we have a multi-threaded algorithm which could do 2 integrals in OpenCL innermost and 2 outermost integrals in C++, why this adaptive 2-dimensional Gauss-Kronrod that we invented. It looks nice, it looks promising. We would love to see this on GPUs, and hopefully this will happen. We test this on GPUs. The accuracy is excellent so far. So I would like to thank Mate and Daniel for a lot of help with GPUs in general, and how to think about and how to program for them. And also Gergely and the Institute for providing support for this work. And I think I should one more. No, it's not more. Okay, that's irrelevant. It's a backup slide. Okay, great. That's it. Thank you very much.
Okay, any questions to the speaker?
No, perfect.
Okay, one question there.
So why are you tied to 61 points Gauss-Kronrod? Where does this 61 you can choose any number basically.
You could.
The integration scheme should work with any
Yes,
number.
you could. And in fact, in GSL, where is it? It's okay, it's one more slide, but I guess. Okay, so in GSL, you have just what is implemented. So the lowest order formula they implement is 21 point. And they go up a couple steps, and then you get 61. So we just choose the highest order because we hope that if your function is smooth enough, that converges fastest. Now, of course, if it's smooth enough. If it's not, then it's not. So we didn't actually try to switch it. But for GPU, since I'm not wedded to this idea that I do 2-dimensional problem first, I like the higher number more. Because then I can put more in one shot. And if I solve that problem separately, then I could send more work out as one unit. But you're right. I could in principle work out any number here, and the people have done this. Is just not coded into GSL. So I actually don't know what the next order would be. Maybe 120 some points. Yeah. So it's. I mean, at some point it's a trade-off, right? Because if I don't get much more accuracy, I'm wasting my effort on integrating functions which are already smooth enough. But that's why I didn't use the 21 point, because I wanted to have lots of work in one thread.
Okay, and just wondering, Mark, if the code doesn't compile, there's the build log, which you can ask for, which has the compilation error message.
Perfect.
But we'll get to that.
Yeah. Good.
Okay. Okay, so let's thank the speaker again.